All right, back at it to finish up this chapter. The next part of the problem-solving literature is going to focus on kind of the classic cognitive psychology of information processing. This is an area where the whole cybernetic information processing view and the development of artificial intelligence, developing alongside early cognitive psychology, has really made its mark. The idea behind early computers in general, challenges faced by people like Alan Turing, especially back in World War II, was that they wanted to design a machine that could solve problems. One of the things that Turing was working on was trying to work on developing a computer that could be a code breaker. And once he manages to work out a way of imagining how this could work, he then proposes the possibility of, would it ever be possible to design a computer that could do more than just that one thing, right? So it's one thing to write to design a computer or even develop code that solves one specific kind of problem. And of course, we've talked about problem solving can be fairly rigid domain specific algorithms, right? But we also know that humans are can do other things. We can solve broad problems of various types of categories and so forth. And so we might think that the human mind is really something that we could call a general problem solver because we can, of course, solve broad categories of problems and solve lots of different kinds of problems. We are not limited to just working in one specific domain. But a lot of early computer programs were. So could we develop a general problem solver? And this is where Turing envisioned the idea that if we could do such a thing, then this would mean that we've created a form of intelligence, but it would obviously be a form of artificial intelligence. So this, of course, leads to the whole, AI revolution. And of course, through the 1940s and 50s and into the 60s, we've talked about some of that stuff with the perceptron model back in the perception notes. A lot of AI development really started to take off. And you might wonder if all of that stuff happened back then, why is it only now in the last couple of years that we're really starting to see major advances in these deep learning kinds of algorithms that give us the modern large language models? Well, that's because our understanding and our research in AI hit something of a sort of a roadblock in the 1970s, and this led to something called the AI winter, in which there really was just not a lot of meaningful progress on these problems until we get into the really into the 1990s. But even post year 2000, I think really things started to accelerate once more. That's a whole separate issue. We don't need to get into that. But of course, let's talk back again about Alan Turing. So when Turing sort of envisions the possibility that it could be possible to eventually make AI, this is where we start to ask questions. How would we know if we created an AI? This is where Turing develops his famous Turing test of AI. This is the example here is that we're supposed to imagine doing essentially something of a quiz of an AI versus a human. So imagine you're sitting down at a computer and you have two chat windows open, and one chat window is communicating with an AI and the other is communicating with a person, and you're supposed to just interview and ask questions of both of these entities to figure out which one is the AI and which one's the real person. And in the early days of computer coding of these kinds of so-called chatbots, the chatbot could really only give answers that were pretty inflexible. And so the idea is that over time, this device would start to be repetitive and its answers would not always be kind of really exact answers to the question. It all felt kind of like pre-canned responses. So we would say that from the perspective of the person who's conducting this interview, they can pretty quickly and easily figure out who's the person and who's the machine. So in this case, we would say that the machine has failed the Turing test, right? It has not tricked us into convincing us that it's human, or possibly made it difficult for us to distinguish between the human and the machine. It's a whole another question when it comes to talking about modern chatbots and LLMs, right? But that aside, we want to focus on the problem solving picture here. So We move into the 50s and 60s, and this is where Newell and Simon were working on developing a general problem solver, GPS. So this is maybe you might don't get that confused with the global positioning satellite GPS, right? This is the general problem solver GPS. And one of the things they wanted to do here is they wanted to create, so again, the idea is how do we create a machine that can solve more than one kind of problem? And what they had to do is they had to separate the knowledge that's required to solve the problem, which might be domain specific, away from the strategy that could be used to solve the problem. And it's that strategy that they developed here. So we'll call this a heuristic, but the heuristic is called means ends analysis. So here's the idea. What is means ends analysis? Well, what they're doing here is they're defining what's called the problem space, right? And the problem space is defined as having a series of possible states and positions in this space. And one of those is the so-called solution state, right? And the solution state is our desired end state. Right? That's where we're trying to get to. But we're not there yet. So there's a distinction between our current state versus the desired state. And our goal is to reduce that difference. So what we need to do is we need to perform some sort of operation that will reduce the difference. And this is called means ends analysis because what we're doing is we have a desired end state and we're now trying to figure out what is the means that gets us to the end, right? And so engaging in means ends analysis, that is applying some operation that gets us closer to our goal, is a very, very broadly defined heuristic here, and it doesn't depend on the nature of the problem, right? So if my problem is to figure out how to drive from one location in town to another location in town, I can use means ends analysis to reduce the difference between current state and desired state, right? If my goal is to decode, all right, if I'm touring and working in the war and I'm trying to decode enemy messages here, then the desired state is to fully decode the message, and my current state is I don't know what the encryption pattern is. But if I continue to apply this operator over and over again, maybe again it can do this job of getting me closer to the desired state. So again, the means ends analysis is a strategy that works across many different domains. That's the critical insight here, right? And that makes it very, very appealing because now the argument here is that this is a way of solving problems in a much more general way. And so, of course, we still have to execute this problem. And of course, that means we have to know which operators are going to be the most useful operations to apply. And that means we have to know something perhaps about what's an effective way. So it works, but excuse me, it doesn't necessarily work perfectly. So one of the choices that this type of approach has to do is it has to figure out a way of figuring out what's the best operation to apply right now. What's the one that's most likely to reduce this difference between current and desired state. One way to think about how that's a challenge is to imagine how a brute force algorithm works, right? So I think I have that on the next slide. I do, right? So the idea of a brute force algorithm is that rather than kind of an intelligent sorting of operations, we're just going to try all possible outcomes, and then we're going to pick the one that works, right? So I've defined it there as a series of if-then statements, but let's imagine, here's another problem that we might try to solve. Well, let's go back, actually, before I talk about that, let's go back to the encryption issue, right? So if we are trying to decode enemy messages, one way to do it is to pick, let's say that what we have is we have a bunch of letters that are part of a text message, and they have been converted through some encryption procedure into other letters. And so the mapping from intended letter to encoded letter is one that we don't know. It could just be advancing one step forward in the alphabet. So if I'm trying to write the letter A, I'm just going to write a letter B, right? Now, that's not a very sophisticated method of encryption. I could make it a little more complicated by jumping 8 letters ahead in the alphabet. But again, that's not very sophisticated. But what if I have a more complex mathematical process where I take the letter A and then I run it through some complex mathematical thing to determine how many steps forward I need to go. And then it generates the encoded letter. And I apply that to every letter, and then I have a very complex mapping here. So I could do means-ends analysis, but it's hard to know exactly what the best choice is always going to be to try one mapping after another. But what a brute force algorithm does is it tries to calculate all possible combinations of mappings and or encryption, procedures, and it just tries one, and if it generates an intelligible output, we've solved it. But if it just generates gibberish, we got to try again, right? And so the if then statements kind of flow like that, where it would be like, okay, try this process. And if it generates success, you're done. If not, try the next decryption process, right? And if that one works, you're done. Otherwise, keep going, right? And so this kind of if then else kind of logic where if this works, then stop, else keep going, right? Then that could take a long, long time, right? Now this shows up. The example I was going to give was playing chess, right? So the idea here is that you can play chess against a computer opponent, and a brute force way could be that what happens is that I make my move, and then in the computer's memory here, for the computer opponent, what it's going to do is it's going to simulate its next move by picking a move and then running through all of the possible combinations of outcomes to determine the likelihood of winning the game from that move. And then once it calculates maybe some sort of percentage of likelihood of winning for that move, it does this for all of the other possible moves that are currently available to it. So you can imagine this might take a long time as the computer has to simulate millions and millions of possible outcomes here. And that's just in response to my first move. So it finally chooses a move and it does something. And then I make my second move. And now again, it has to repeat its brute force simulation. Obviously, the constraint space has maybe been reduced a little bit because pieces have moved. But nevertheless, that's how such a process would work. And it's not very effective, right? And so these kinds of approaches to developing, say, computer chess processes didn't really work for a long time when it came to trying to beat an actual human expert chess player. If we fast forward to the 80s and 90s, we get John Anderson's work on what's called the ACT or ACT model, which stands for Adaptive Control of Thought. And this helps us maybe get a little insight into some of the limits of means-ends analysis. So one of the things I said before is that with means-ends analysis, we want to have an intelligent way of choosing the most effective operator. And well, how do we do that? Well, one way is that we really need to think about knowledge, right? One of the things that means-ends analysis did was it tended to separate the knowledge that we have about the problem versus the procedure, which is the means-ends analysis. But Anderson's model is also going to bring that knowledge back in, and he's distinguishing here the kinds of knowledge. One is declarative knowledge, which is our knowledge of facts and important and relevant pieces of information. And then there's our procedural knowledge, which is our knowledge of how to actually incorporate those facts into a series of steps for solving problems. And so having these two levels of representations of types of knowledge here, the idea is that his approach here is to say that what we really are dealing with here is a system that takes factual or declarative knowledge and converts it into procedural knowledge. Now, as a way perhaps to get a good insight, hopefully a good insight, into the differences between each of these is to now have another kind of example. And we're going to see how each one of these would apply here. So let's say you've bought some furniture. You got some IKEA furniture, right? It's all in a box. You got your parts. But it didn't come with the instructions or you've lost them. So now you're going to have to try to figure out how to put this thing together without the instructions. So, of course, we can define the problem space. We have a desired end state, which is the fully assembled piece of furniture that looks like it does in the picture on the side of the box, if we have that to go on, maybe. Or at least we have some knowledge of what it is that we've bought. It's a bookshelf, so I have some knowledge of what a bookshelf is supposed to look like in its final form, right? Or a desk, again, I know what that's supposed to look like. But I'm in the current state, which is a problem state because I'm not there yet. I just have all the pieces laying out on the floor in front of me. So let's try a means ends analysis, right? So again, what I'm going to do is I'm going to look at the picture, or I'm going to consult my mental picture of what this thing is supposed to look like. And then I'm going to think about breaking it down into smaller bits and pieces, right? So I'm going to say, okay, well, I know if it's a bookshelf, I know that there's going to be parts that are the shelves, and I know there's going to be parts that are the sides and then maybe the top and the bottom, and maybe it has feet or legs at the bottom. So I can break it down into smaller subgroupings of parts, and then I'm going to go try to find those pieces and sort them together and try to figure out how they go together. And so by doing that, what I'm doing is I'm applying this operator bit by bit. Let's assemble this part section of it. Let's assemble this other section of it and see if we can make that all go together. And hopefully it'll all work. But if I hit a roadblock, one thing I have to do is maybe I have to go backwards. I have to undo some of those steps and try again to adjust and find my way through. But what I'm doing is I am essentially navigating this problem space, and if occasionally hit roadblocks and have to reverse course and try another pathway, but eventually I will get to the end. It might not be a very fun time, but eventually I will solve my problem, right? Now, even less of a fun time would be the brute force algorithm, which is I'm just going to start putting pieces together in random configurations, and and I'm going to keep repeating this until one of them finally gets me the configuration that looks like the correct outcome. No one's going to try that, so we'll just move on past that, right? But then the idea is that if I take the ACT approach, what's going to happen is I'm going to look at each one of these parts and I'm going to think about their functions, right? Again, this is a shelf part, so it has to be horizontal to hold the books or whatever I'm putting on the shelf. This is a structural part that needs to be more vertical. These bolts or screws or nails have to go in certain places because they hold things together. So again, I have to have some kind of declarative knowledge about how everything works. I also have to have procedural knowledge about how to, the order. Maybe I have to build it like bottom up, right? So you start with the bottom pieces and then add the tops onto it bit by bit. So that could be a procedural approach. And then, of course, that still doesn't mean everything happens perfectly. So when we encounter a mistake and things aren't working and I can't figure out what to do next, or some part doesn't fit because of some error in my sequence, then again, I have to pause and think about some fact or procedure that could have been done differently. And that gives me the insight I might need. Insights may be a bad word here considering our previous video, but it gives me the next choice of an operator to try next, right? And so in this way, one of the things that this ACT model does is it helps us sort of think more about expertise a little bit, because we want to think about when we are solving problems, people can develop expertise when it comes to solving problems. But what is it that actually makes someone an expert problem solver? And the ACT model is going to help us understand that maybe one way to think about this is about the knowledge structure that novices have versus experts, right? And so the argument here is one way to think about that is that novices have the declarative knowledge. They can learn a bunch of facts, like you can take some classes and learn some basic facts, but that doesn't necessarily make you, let's say you're going to medical school, right? So you can take classes and you can learn a bunch of facts about human biology and physiology, but that doesn't mean you can step right into a physician's practice or a hospital and start doing it, right? You need some other stuff, right? You need that hands-on experience, working around other professionals, to learn how those facts actually translate to daily clinical practice, right? And that's your procedural knowledge. So in that situation, the difference between the declarative and the procedural is an extra step, right? It doesn't come just from knowing the facts themselves. And part of it then is also about pattern recognition, right? So what happens, this comes up even in these medical kinds of situations, is that you have a patient that presents with certain kinds of symptoms, and there's, you can consult a list of symptoms, but that's not really how diagnosis works when it comes to that, right? We don't just plug all of the symptoms into a list and say, well, it matches this list, so the patient has blank, right? We need a little more complex pattern recognition here. We might need to recognize that sometimes certain symptoms are very important and have a high level of relevance to the diagnosis. Other symptoms might not be important at all, right? When people tell you about their symptoms, they might tell you about everything that they're thinking about and feeling, but that doesn't mean that everything they've said is relevant to what's really wrong with them, right? What's also relevant is a person's medical history, right? And that's why when you go to the doctor, they start asking you questions like, have you been out of the country in the last blank number of weeks or months, and all these other things. And they always ask for your family history because that's all part of the larger picture here, right? So an experienced physician can capture all of that and recognize that as a pattern, whereas maybe a med student would struggle in that domain, right? Um, and that also represents our chunking. So when we talked about short-term memory and working memory previously, we talked about chunking. And chunking can be done in expert level ways. We talked about chess playing when we talked about short-term memory chunking, right? And how expert chess players can look at the layout of pieces on a board and better remember all those locations. And that's largely because they are capable of meaningfully seeing a pattern there and they can see the strategy, and this helps them remember more information. So they take a more expert level approach to it. That then reduces your cognitive load. It reduces how much information you have to remember. So in this case, then that actually is an aid to problem solving when you have less of a load on your memory systems as well. And of course, one of the things that's important is that problem solving often happens in a dynamic environment where the context and the situation can change, and being able to adapt to that is an important part of it. And again, experts are a bit more flexible and can adjust to changing information and changing circumstances. Now you're going to note that I have a asterisk on the practice part here, right? So chunking reduces our cognitive load, but so does practice. And so we need to talk about practice, right? So clearly, in order to become an expert problem solver, uh, one of the things we're going to need to talk about is that expertise tends to be very domain specific, right? So even though, as I described earlier, humans are pretty good general problem solvers because we can solve lots of different kinds of problems, when it comes to actually developing true high-level expertise, that means you can be a world-class problem solver at a specific kind of thing. That requires a lot of time and a lot of practice and a lot of coaching and a lot of effort. And that's not going to easily generalize to everything else. So somebody who is a world-class chess player isn't necessarily also a world-class physician who can diagnose complex disorders, right? Because these are very different domains, and all of the time and effort that went into practicing playing chess doesn't generalize or transfer to the kinds of problem-solving knowledge, whether it's declarative and or procedural, that is required for diagnosing disease. Now, you may have heard of this 10,000 hour rule business, right? That it takes a lot of time to become an expert. 10,000 hours is a lot of time, right? Now, is it true? Well, not really. I mean, let's say there's a nugget of truth here. Time is important, right? Where does it come from? Let's talk about that, right? So, up at Florida State, and Anders Ericsson, um, he and the rest of the team up there, they were looking at people who were high-level experts, right? In this case, they were looking at expert musicians, like violinists. And one of the things that they found when trying to understand what is it that these people all have in common that would be like that makes them world-class expert musicians compared to other people who are not, who might be about the same age, but they're just not that high of a level of performer. One of the things they noted is the difference in how much time they had dedicated to their craft. And so they had just sort of reported that they all had at least 10,000 hours of practice. That's an easy take-home message. And so the author, Malcolm Gladwell, published a book in which he sort of made a big deal about this and called it the 10,000 hour rule and suggested that that's what you need to achieve that high level of performance. But that's really a misrepresentation of what Ericsson and the rest of that crew were really doing. What they were really focusing on is 10,000 hours of deliberate practice. And that means we need to think about what does deliberate practice mean, right? It's not just about repetition. It's not just sitting down with my violin and going through my exercises day after day after day after day until I've accumulated 10,000 hours of those exercises, that doesn't make me a world-class violinist. What I need is I need what is called effortful practice with feedback. So what's going on here? What that means is that I have to have a goal. When I start practice, it's deliberate and effortful because I'm approaching my practice with a goal that there is a skill, an incremental skill that I'm trying to get to, right? I've achieved some level of skill, but there's something in front of me that I still haven't, but I'm not there yet. And so I'm going to approach my practice with a specific set of practices and exercises that are designed to get me closer to that next goal, right? And so I need the feedback to know if I'm getting closer or not, right? And then once I hit that goal, I need a new goal, right? And that means I need that goal setting that needs to involve then identifying the parts that I know how to do versus what still remains. That then typically means that feedback and that revised goal setting and identifying weakness requires me to have a coach, right? A teacher, a coach, a mentor, somebody who knows more than I do, who knows then what I don't know, because that's part of the issue here. It's one thing to just sit down and read a book about something and learn what's in that book, and you can learn some things, but that doesn't mean you know everything. And knowing what you don't know so that you can go out there and learn those things is a subtle but very important missing point. That's where teachers, mentors, and coaches become very, very critical here. So the quality of the practice there, right? Having that feedback and the revised goal setting, that is very, very important. So maybe 10,000 hours is relevant here, but it's 10,000 hours of deliberate, well-mentored, well-coached practice, not just sitting by yourself, repeating the same routine exercises over and over again. So that's pretty important. What are some other ways we can think about improving with practice? So one is to talk about how people are different from each other. Is it possible that some people might just be better suited to becoming a world-class musician? Other people might be better suited to becoming a world-class athlete or a world-class scientist or whatever it might be that they could develop their expertise in. And so we might think that we're all a blank slate. And what really matters then is just uh, your openness to working and trying hard. This is where the research of Carol Dweck comes in with this idea of the growth mindset versus the fixed mindset. And the argument here is that we want to encourage people, especially children when they're still in school, to have a growth mindset. And a growth mindset is focused on this idea that I can do anything as long as I set my mind to it. And I just need to be open to trying and working and being industrious and getting better and improving. And as I have this right mindset, then I'm going to improve in whatever I set my mind to. And this is contrasted with the fixed mindset where the person has this kind of perspective on their self or a self-concept where they're just saying, I am who I am, and that's it, right? And these things can't be changed. There might be a certain appeal, I think, when we think about this to say that, okay, sure, it seems better to have a growth mindset. But one thing that's pretty critical is despite the popularity of this approach, especially in educational research settings, a lot of recent studies, especially meta-analyses, have looked at the interventions that have been done. Because one thing we could try to do is try to create an intervention to get children to be more likely to adopt a growth mindset early on. So the next question then is, do those interventions pay off? That if we can successfully get children to adopt a growth mindset, are they more likely to go on to bigger and better things? And individually, little studies here and there tend to point to this and saying, yeah, there's promise here. But what a meta-analysis is that you look at the sum total of all of the papers that have been published on this, and let's look at the findings. And oh no, it turns out it doesn't really hold a lot of water here, right? The effects are fairly small and not very compelling. So a person's mindset might not be a huge issue here. Something similar might come from the personality traits, right? Is it possible that your personality makes you more suitable for certain kinds of positions or domains or skills where you should have better alignment to that. And again, the effects are pretty weak. Although one thing is, again, one of the traits that are most commonly discussed in the five-factor theory that includes it's the OCEAN acronym, right? Openness, conscientiousness, extroversion, agreeableness, and neuroticism. the openness trait, open to new experiences, that could potentially overlap with the growth mindset business. But to whatever extent that it does, if the growth mindset doesn't make a huge deal, then openness as a personality trait is not going to be a big deal either. What about just overall intelligence and IQ? Yeah, that's ones that's we're a little bit a rough predictor there, but we're just going to hold off on that till we get to that chapter. Now, this other question about innate talent, right? Is it possible that it's just possible that some people are going to be better at certain things because that's what their genetic predisposition is? Well, the answer here is maybe. And this is kind of interesting because if we think that people are a blank slate, then what that means is that they could become anything they want to, right? And we see a lot of this kind of stuff because there's a lot of parents who want to make their kids great at something, right? And the parents might pick what that something is. Like, I want my child to be a great musician, so I'm going to start getting them piano lessons when they're 2 or 3 years old. And I'm going to make sure that they get fully immersed in that at the earliest possible age because I've learned from some neuroscience stuff that I've read somewhere that the brain is very neuroplastic in our early childhood. So that means that if we get them immersed in this stuff early on, then it's going to restructure their brain and rewire their brain so that they can develop the highest possible level of expertise and high level of performance at playing this musical instrument. And that's how I'm going to make my child great, right? And if it's not that, maybe it's sports and athletics. But again, I'm going to start them at the youngest possible age, and we're going to go from there. So again, what the research has looked into is what it's sort of like what Erikson was doing, where let's go find these people as adults who have achieved this super high level of world-class performance, whether they're musicians or athletes or what have you. And let's find out, is that the factor that they all have in common, that they all got exposed to this at a very super young age? And it turns out, no, it's not, right? What's really going on here is that what these people all have in common is that in their early childhood, they had access to a very broad range of different kinds of activities. And that exposure to all of the many different kinds of things gave them the opportunity to discover the one thing that they were actually good at. So it wasn't just being forced into one particular pathway at a very early age. It was really about being given the opportunity to explore and find something that fit with what they were naturally good at, apparently, right? Now, what that natural tendency or innate talent really is and how that works genetically or epigenetically is not at all quite clear, but it does seem to suggest that we're not just a pure blank slate and that any 2 or 3 year old child could be pushed into some domain and just forced to become an expert there, but rather children will explore. And when they are given more opportunities and find the thing that really fits them, that's where you're going to have more likely long-term payoffs to developing high level of performance. So that relates to our last point on this slide about the environmental factors here, right? So as I described with deliberate practice, we need a good mentor or a coach that can help us revise our goals and give us good feedback. And we need those opportunities to find where we fit in life, right? Okay, last thing to wrap all of this up here. We were talking about medical diagnosis earlier, and that's a domain that requires some level of expertise, and we can see how another approach to reasoning can help us out here, and we're going to use medical diagnosis as sort of the test bed for this. So forward and backward reasoning. This is actually induction and deduction, which we've talked about. And so the idea is that inductive reasoning, forward reasoning is going from specific cases to a more general conclusion. Backwards reasoning is starting with the general conclusion and then working backwards to the specific cases here. And we could use either one of these when it comes to solving a problem like a diagnosis problem here, right? So, okay, let's say that you're a doctor and your problem is that you have a patient who has symptoms and so you need to determine what their diagnosis is. Obviously, you could go through means ends analysis and brute force things, right, where you're going to try to like just randomly treat them and see if that makes them better. That's not a good idea, clearly, right? So what we're going to do here, let's try forward reasoning. So forward reasoning is defined as reasoning from the symptoms to the diagnosis. So here the argument is that what happens is I'm going to think, okay, let's do a symptom list, right? And I'm going to consult a list of symptoms, and that's going to then I'm going to reason from that to the diagnosis. If I'm engaging in backwards reasoning, what I'm going to do is I'm going to consider a likely diagnosis, and then I'm going to look at the what that diagnosis would expect when it comes to the symptoms. So then I'm going to look to see if my patient is actually having those particular symptoms. So here's how this works in the experiment that was actually done. They took some people who were all medical doctors, physicians, but they have different specialties. So here's where expertise becomes an issue here, right? Becoming a physician makes you an expert in a lot of aspects of human pathophysiology, but there's also the fact that physicians develop specialties. So their expertise is really, really highly domain specific. So you have a cardiologist who is an expert about things related to the cardiovascular system, and then you have an endocrinologist who is an expert about things related to the endocrine system and glands and hormones, right? In this situation, they were given case descriptions of patients, and then they were asked to think aloud. This is an actual protocol when it comes to studying problem solving, is we ask people to think out loud so we can try to figure out what are the steps and things that they were going through as they solve the problem, and in this case, arrive at the diagnosis. And what we find is that when they were presented with a case that was within their own specialty, so a cardiologist was given somebody who's having cardiac problems, or the endocrinologist was giving someone who's having some endocrine problems, then what happens is that we see them engaging in forward reasoning, that they are looking at and seeing the pattern in the symptoms, and they move forward to the diagnosis. But when they are given something that is outside of their specialty, they are not so good at recognizing those patterns. So what they instead do is they recall some things like, okay, I know this particular pathology exists in that field, so maybe this could be an example of that. And so they work backwards here to say that, okay, I think some of those symptoms must fit that. And of course, when they're going in a forward way, they made accurate diagnosis. And when they were working in the backwards case, they were more likely to be inaccurate and make mistakes. So again, we see here that the level of pattern recognition that's happening here was enabling forward recognition when you're working in your own expertise, or forward reasoning, I mean to say, when you're working in your own expertise. Okay, well, that is it for this chapter finally. So we will call it here. Let me know if you have